Welcome to the Big Bang. In biomechanics, it is very important that we understand dynamics and kinematics to better study the motion of particles or points in our bodies. These particles can move in straight lines following a 1D rectilinear motion, or they can undergo curvilinear motion in 3D along curves, or angular motion, which is also in 3D but measured using radii and angles. To begin studying these motions, we need to review the basic understandings of velocity and acceleration. If we have a particle at point P naught that moves towards point PF, we can draw vectors to its origin point, capital X, and to its final point, small x. The difference between these two vectors will give us the particle's displacement, which can be written out as delta x. The velocity can be calculated as we take the limit of delta x approaching 0 of delta x over delta t. That's simply dx dt, or x dot. You will often see this notation with a dot for the line derivative in the study of particle kinematics. All that means is that you are taking the derivative with respect to time. The acceleration, on the other hand, will be the limit as delta t approaches 0 of delta v, the velocity, over delta t. That's the same as dv dt. We can also write that as v dot or x dot dot for the second derivative with respect to time. Sometimes you will be given acceleration or have to find the acceleration as functions of different variables, time t, position x, or even velocity v. Solving for these accelerations can take some getting used to, but they're quite straightforward once you get to know them. To write out acceleration in terms of time t, we just have to remember that acceleration equals dv dt. Multiply both sides by dt. We get at dt equals dv. Then integrate both sides to get the final expression. You will have the integral from 0 to t on one side and from v naught to v on the other. The acceleration in terms of x will involve remembering that a equals dv dt and v equals dx dt. Starting the proof with v dv, you want to multiply it by dx dx and dt dt. Then remember that dt dx is 1 over v, the velocity. That helps us simplify the expression out. Then you're left with noticing how dv dt equals a. You end up with v dv equals a dx. Now integrate both sides and you will get your final expression. On one side, the integration goes from v naught to v, and on the other, from x naught to x. Finally, to get a in terms of v, you need to once again remember that a equals dv dt, rearrange this equality such that a is on the same side as dv, then integrate both sides to get your final expression. You will integrate the dt side from 0 to t and the dv side from v naught to v. Notice that the left side equals t. Another way is to use a equals to dv dt again, but now you multiply the dv dt by dx dx. We can then begin to simplify the expression. dx dt equals v and dv dt equals a. So we end up with a equal to v times dv dx. Since a is a function of v, we move a to the same side as dv and move x to the left. Integrate both sides and voila! The left integration goes from x naught to x, and the right integration goes from v naught to v. Now you have another expression where a is in terms of v. Okay, enough of that for now. Another very important thing for you to understand is how to calculate the tangential and normal accelerations. Picture a particle moving along a path with arc length s. The coordinates of its motion would have et tangent to the path and en normal to the path. To get the tangential and normal accelerations, we can start from the velocity. We know the velocity equals dx dt. If we multiply that by ds ds with ds as a differential arc length, we can represent v with its tangential component, ds dt, is really the speed along t, while dx ds is the unit tangent vector. We end up with v equal to vt times et. We know that the acceleration is dv over dt. Since the velocity is vt et, let's write vt as ds dt, then multiply that by et for v. Take the derivative of this v expression and we get two terms that add up to give you the acceleration because of the product rule. So now let's play with the second term and multiply it by ds ds. We end up with the first term unaltered and ds ds squared times det dt. For reasons we will not go through in this proof, det over dt equals en over rho, where rho is the radius of the curvature of the path. From here, we can rewrite the expression highlighting each acceleration component, the tangential and the normal. Notice that d squared s dt squared is the derivative of the speed and the derivative of the absolute value of the velocity. Similarly, ds dt squared is the speed squared or the absolute value of the velocity squared. This actually ends our journey as it gives us the tangential and normal components of the acceleration. The giveaway should be that there is an et multiplying one term and an en multiplying the other, but you should get the idea by now. I will see you next time.